Thanks, Keith. I used to really enjoy coming down here and hanging out with all the CRPC buddies and Ken. I miss him dearly. And thanks to Jan for his leadership and finding the coffee for me this morning. Okay, I better put this in my pocket. So this talk is a bit of everything. I mainly designed it for me to make it fun to give. Hopefully it'll be fun to listen to. You reach a certain point in giving talks where it's all about having fun. Okay, so I'm going to talk about this integration of simulation, data, and machine learning in the context of where we're trying to go in exascale computing. And I'm going to start with this one slide that has two application areas that people in my lab are working on. The first one is this idea of computational cosmology, where we're in some sense treating, was that me binging? No, something. Treating the universe as a dynamical system, and on the left, starting with Einstein's theories, building models of mock galaxies, or as Salman Habib likes to describe, simulated sky. And sky here means, stars and galaxies, not clouds. And then, so building these simulations, and then driving these to be consistent with observations. Initially, data coming from things like the Sloan Digital Sky Survey, and in a few years, coming from the Large Synoptic Survey Telescope down in South America. So this is the idea that we're bringing large-scale supercomputing meets large-scale data, and there's an iteration at this joint, okay? And this is not dissimilar from many fields of science. If you look in materials science, we have something that's somewhat similar. So on the left-hand side here, we've got theory that's building up an electronic structure model of some material and predicting scattering results, taking that material, dropping it in something like the Advanced Photon Source at Argonne on the right, taking a sample, taking experimental scattering, and looking at the resulting, say, phase diagram, and trying to reconcile these two things. So these are cases where today, right, we have relatively traditional methods of gathering large-scale data from sensors, data analysis methods on that data, building some kind of compressed representation of the output, and reconciling that with simulation. And I'm not going to use my iCloud here. Go away. Sorry, my computer is, I'm going to take it off the network here. Jerome's being too friendly. Okay, but something happened along the way, right? So pretty much everybody in this room has probably not been asleep for the last 4 or 5 years, and you can't help but notice that something is happening in the AI space that maybe many of us have dreamed about for 20, 30 years, but suddenly in the last 5 years, there's been this exponential growth in the use and driven by the utility of things like deep learning. And this is a plot from Google software repository. So somebody ran a script over the internal software repos at Google and counted how many projects in the repos were doing some kind of deep learning. And so it's a relatively good kind of raw measure of the growth. And I think somebody redid the experiment this year. We got over like 4,000 projects. So there's been this kind of rise of deep learning. And the market is kind of paying attention to this, right? So the broad notion of shifting investment patterns and growth. So if you believe these market forecasts, IDC is predicting that machine learning is going to be something like $40 billion in 2020. And of course, you could kind of predict that anyway if you look at the merger and acquisition kind of activity of companies like Intel and so on, that they've probably spent already $20 billion acquiring companies. And the deep learning subset of this is maybe going to be $5 billion by 2020. And there's a huge battle for mind share in this space, right? So this was from the spring GTC conference in San Jose, where Jensen got up and talked about the V100, and for only $169,000, which is kind of like 2 Teslas, I guess, you could get a DGX1 with 8 V100s, each of which is 18 billion transistors in it. And I was joking with Jan at breakfast or at coffee this morning that I got one of these in my office, which is the new DGX station with 4 Teslas. And of course, it's $70,000, so it's about the price of 1 real Tesla. But the beauty about this thing is it's liquid cooled and it's absolutely quiet. So it boots up a little bit noisy and then it settles down to like less than 20 decibels. So it's like, it makes less noise than like your cell phone charging. And it has a half a petaflop of compute and half a terabyte of RAM and a bunch of solid state memory in there. So this is like I don't know, how many people in here growing up lusted after very powerful workstations? I'll tell you what, yeah, okay, right. So this is like the new lust object. And in fact, they're made down here in Houston, and ours got delayed by the flood, so we're like one of the first ones out of the box. And of course, Intel is hot racing in this space as well. So this is a picture of Raj at ISC talking about AI on the Intel architectures, and so there's this kind of epic battle of the titans, happening, where Intel is trying to outflank NVIDIA, and NVIDIA's printing money with GPUs. We have a machine at Argonne that's based on the Intel KNLs, for which we're doing a lot of deep learning. I'll say a little bit more about kind of acceleration strategies, but I wanted to put a plug in here for Cray, who's one of your sponsors. So thanks, Anthony. Okay. All right, so if you're trying to understand what's going on, and I know there's probably some students in here, this is a plot of job advertisements from monster.com, okay? And it gives you a pretty good forward indicator of which companies are positioning themselves to dominate the world. And you can tell that Amazon is really outflanking even Facebook and Google in this space in terms of how many openings they have in machine learning, deep learning, and AI in general, which is kind of interesting. IBM is still in the game, of course. Apple's trying to catch up, and Microsoft. So I thought this was pretty interesting because this is not, if you go out and just ask your students, they wouldn't actually echo back this picture, right? So I think that's quite interesting. I can't help but do the compound annual growth rates against these different segments. So, I came out of the HPC world, but before that I did automated theorem proving in math. So we tried to do AI back in the 70s and 80s, but our machines sucked. So then we did parallel computing because that was more fun, because things didn't suck as much. And now we can go back to doing what we originally started out to do. But if you look at HPC, it's right now, in 2020, they're estimated to be about a $30 billion market, but it's growing, kind of like the same scale as the Chinese economy, right, about 5%. Data analysis is growing faster, and it's bigger because it sweeps in more general, data center type stuff, maybe growing at 11%. And deep learning is kind of growing like crazy, 65%, but it's still pretty small, say, in 2020. Of course, this is completely non-scientific, but if you just extrapolate those curves, you get funny things happening, right? So deep learning becomes bigger than high-performance computing in 2024, and it becomes bigger than data analysis in 2030, right? So this is kind of interesting. I don't know if it's, anything like that's going to happen. But what we see as a big picture is that those 3 market segments, in some sense, are all the same people. So people in this room, I mean, we just kind of slosh around from wherever the funding is at some level and where the interesting problems are. And so what I see is the applications are moving more towards a position where they can leverage each of these three kinds of activities or capabilities. And we're starting to see this happening in cancer and cosmology, materials, climate, drug design. I'll quickly walk you through a couple of examples here. So in climate, machine learning is starting to take off. It's initially being used largely in things like statistical downscaling. So what that means is where you have a climate model maybe that's simulating global climate at, say, 10-kilometer resolution, and yet you're interested in what's going to happen in congressional districts, okay, which might have a finer resolution. And so in order to make a prediction, you'll do some kind of statistical model that correlates weather patterns at a much finer scale and then use that climate data to drive those statistical models. So that's already been happening. This is what is giving the weather nowcasting really accurate forecasts in very local regions. We're seeing people applying machine learning to scale down sub-grid scale physics, where historically the pattern in climate would be to spend a ton of time trying to research like cloud, droplet microphysics, and then write a physics module in the climate model that tries to empirically capture that physics, even though the climate model resolution, that thing maybe try to do resolution in microns, and yet the grid scale is kilometers, right? And so you do this kind of sub-grid scale averaging. One of the new techniques is to write those little models, run them through a whole range of parameter settings, and then learn a simple distribution and replace that sub-grid scale empirical model with I guess you could also call it an empirical model, but a machine learned model of that function, which might be simpler, cheaper to evaluate, and so on. You have people trying to do direct estimate of climate statistics, discovery, and output. This one I find particularly interesting. So the climate has these antipodal moments, so points on the surface in space and time that kind of co-vary. And the most famous one is like El Nino effect, where you have a warming and a cooling that kind of relate to each other. But people have been searching for these, and they found new ones using machine learning, somehow down in Australia. I don't know what it means. We're applying stuff like this in genomics, which I could talk for hours about, but won't in this talk, but maybe at the break. We're applying it to predicting phenotypes of microbes, where we have the genome. We've never seen the bug, never grown the bug, but we can predict what it grows on and whether it's resistant to antibiotics. More recently, we're doing a lot of work in cancer, and I'll say more about this, but cancer is a very rich target for machine learning right now in diagnosis, outcome prediction, drug response prediction, imaging, et cetera, et cetera. So I'll say more about that. In drug screening, this is an area that I worked in for many years using kind of classical methods where we build models of proteins. We do drug docking or protein mechanics simulations and try to do what was euphemistically called rational drug design. I much prefer irrational drug design. And this tried to penetrate pharma in the 80s. Some of you might remember this. They were getting interested in buying supercomputers, and they deployed them, and they tried it, and it kind of didn't work, and then lost interest. But there's always a contingent in the chem informatics space. That's my phone. That's my TARDIS, actually. I should probably turn it off. It was a little bit early. But what's happening in drug design is people are starting to hit it with, again, machine learning, or in particular in deep learning, that is starting to outperform classical physics-based methods for drug design. And there's this paper that was at the NIPS conference in 2014 kind of laid the foundation for that outperformance, where deep learning models now are generally considered accurate within about 1 kilocalorie for binding computation. And those of you who are, how many biophysics people do we have in here? That one kcal number is the magic number. That's about as accurate as our existing kind of first principles models are. And it's a lot cheaper to do it. So here's some nice little comparison chart here from that paper. This is a couple years old, but this is where they're comparing a whole bunch of different machine learning methods. And of course, it's kind of a, they're kind of pimping deep networks here, but it kind of, trumps stuff. But it's not just in drug design. It's starting to be used across the space in trying to drug discovery. And I'll say a bit more about that because I've been working in that more recently. It's being used in disease propagation problems. So this one, I find this one particularly interesting. So this is an example where Twitter feed was mined for phrases like, I'm feeling crappy today, or I think I'm going to skip work, or my throat itches, or I want to go get drink scotch or something like that. And they use that, those phrases to learn the relationship in time between the spikes of these terms in Twitter and reported incidences of influenza and various head cold phenomenon. And so now from looking at the Twitter feed, you can get about a 10-day window on when people are going to get sick. And so there's probably some way to make money off of this. I'm not sure yet, but it's kind of an interesting phenomenon. That same concept at some level is being applied to coupling climate data with disease and environmental, climate and environmental information with disease outbreaks in Africa. So trying to build a combined risk model that learns the relationship between environmental properties, monsoons, or floods, or drought, and malaria outbreaks, and so on, which gives you kind of a predictive engine for managing disease. Of course, it's being applied in material science to essentially design materials from point simulations in phase space and then synthesizing stuff and then characterizing it. The one that I find that particularly interesting is in the cosmology case. So this ties back to the early one I was talking about with Salman Habib's group. But what they're really interested in is searching for these lensed galaxies. Okay, so in the Sloan Sky Survey data, which was from about 10 years ago, more than 10 years ago, that data set is a few terabytes. It's not that big, really. And they were able to use Mechanical Turk. How many people know what Mechanical Turk is? Okay, so Mechanical Turk is this Amazon service, almost made a mistake, where you can build a little application. Typically it's image-based. They use this for things like labeling images for deep learning. But in this case, they got little snapshots of galaxies from the Sloan data, and it goes out on the network, and you have people from all over the world, typically in developing countries, for a few pennies per 100 images or something. They classify them, and they built some examples that said, classify galaxies that look strange, and the particular strangeness that you're looking for is something like this, and if you squint at this a little bit, the light, it's a little too bright in here, but you can see that there's this kind of halo effect. And this is a galaxy behind a black hole or behind some dense thing, and the gravity is basically creating a lens that replicates the image with some distortion. And so in the case of the Sloan data, it was small enough they could use Mechanical Turk to have humans go through it and find these. But when LSST comes online in a couple of years, it's producing about 15 terabytes of data per night. And it will vastly exceed the amount of capacity. If we were all on Mechanical Turk, we still couldn't keep up with it. So the only way to search this is essentially using machine learning. And then the question becomes, how do we build a training set? So we have all this data from the Sloan, and that's labeled data to train this, but we're also doing these cosmological simulations where we can simulate this effect, we can simulate the optics. So a whole bunch of the training cases are actually coming from simulation. So the network will be trained on real data and simulation data, and then turned loose on the data feed coming from South America every night looking for these events. So this is a trend that we're starting to see in many applications. And if we look across the National Lab System, we're starting to see hundreds of these things popping up. And I mentioned some of the materials we're seeing in fusion reactors. So a really great example of this from Bill Tang and students from Harvard and Princeton, where they're trying to predict disruptions in plasma and tokamaks, basically. And so they've got access to the diagnostic data, and the question is how early before the disruption happens can they predict that the plasma is going to go unstable. And now they're having pretty good luck at predicting it, tens of milliseconds before it happens, which is kind of early enough that you could tweak the magnetic parameters to maybe prevent collapse. So it's starting to become used across the domains. And when we were kind of gazing into our crystal ball and saying, well, gee, this is cool, but we're building these machines as though it's like, 2005, right? And so what's going to change here? And so we're estimating that maybe by 2021, that perhaps a third, or could be more, of our application use on the biggest computers in the country will actually be doing various forms of machine learning, not traditional PDE-based simulation. So what does this mean, really? Well, if we look at the what I call the old HPC paradigm from like 10 years ago, right? We have something like this, and this is the, Jan would kind of nod, and everybody nods and say, we got a big computer running a simulation, and it's producing data, and we do some kind of munging of that data. Depends on what it is. We try to slice and dice it, produce versions of the data that we could then dump for visualization. We kind of stare at the screen, or walk into a cave, or put it on a headset, or HoloLens or something, and we try to make sense out of it, and then we tweak the simulation, and we kind of are in this loop, right? And we've been kind of running this treadmill for a while, and we're starting to see, well, there's maybe a slightly better way to do that, which is to have a helper, okay, plug into the data analysis part. And this is kind of the scenario that I was describing, like in the cosmology and the materials and so on, where we're still doing simulations, and instead of having only a human in the loop, we're trying to add a machine learning component that's kind of looking over the shoulder of the scientist or team and trying to suggest things, right? Oh, like you missed this, or that's not really a cancer tumor, that's something else. But still relying mostly on the traditional visualization loop for making decisions in terms of changing the simulation. And we're seeing this is starting to become more common. But what I think is really going to happen is more this, where the machine learning component is becoming so powerful in some sense, and the realization that we can use it not just to give us some advice, but we can kind of turn control over to it. And so it can make decisions about which simulation to run next. It can interpret the visualization, so we still will generate pictures because the humans kind of want to have a little bit of clue about what's going on, but the deep learning engine is going to be not only looking at all the pictures the humans looking at, but pictures that the humans couldn't even possibly look at, the higher dimensional images and so forth. And we'll be basically running the show, right? So we're seeing this. We can see this is going to happen, and the question is, what are the things we need to do to both, kind of ease it into the world, right? So one piece of this, and I'm going to focus, at least this part of the talk, on these two connections between the machine learning block and the simulation block. So one direction here is embedding the simulation in deep learning. And the reason that I say it that way is that if I look at this picture, I've got bidirectional things happening here, right? So I look at the arrow where the simulation is pointing at the learning. What does that mean? And what it means to me is that the deep learning engine, as it's being trained, wants to ask the simulation questions. It wants to say, well, I've got this data, and some unreliable human has labeled it X. What do you think? And it's going to ask the simulation. So how would we build that, right? So I'll just walk through it here. So the idea here is that the simulation is going to provide hints to the deep learning as it's learning some relationship. And the way that we think about this is that the deep network is going to invoke a simulation, in some sense as an oracle, to give it additional information to augment the training data that it has, right? And it's going to be using that simulation to give it some supervised labels. It might also have data that's labeled with really good ground truth information, right? And of course, the simulation doesn't care if the deep learning is asking it often to answer these things, so it could be invoked, millions of times. And depending on how we tune this, right, the ability for the deep learning to actually converge or to learn could, in some sense, be rate limited by the simulation. And an example of this case is this cancer drug resistance example that I'll talk about here in a second. So this is one model. And to put it in the cancer perspective, because that's what I'm spending a lot of time on these days, and I won't deep dive into this, I have another couple slides in a second, but we have right now models, we can use machine learning to learn a lot of relationships in cancer. We can learn the relationship between gene expression and drug response. We can learn between molecular properties of the tumor and outcome and so forth. But we can't easily explain those functions that we've learned. At the same time, the cancer research community has been deep diving into molecular mechanisms for a long time. And so we have a lot of what I call point models that explain, this signaling cascade does boom, 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 and this signal now gets propagated from the membrane to, this, and is causing the cell to dysregulate in this way. The problem is that we don't have a way to take those mechanistic models and aggregate them up to a global model. That's what the machine learning is doing. But what we would like is to have this thing at the back here, which is a hybrid model that both has predictive performance that we could use in therapy or clinical use, but also has the ability to be interrogated and give us back mechanism. And we don't have that yet. This is a slide I stole from Russ Altman, but this is what the vision is there in cancer. So how would we make headway on that? So it turns out that a few years ago, there were some groups in the deep learning space that created this concept of a teacher-student network model. And the original idea here was that the teacher model was a big complex model that was trained on a ton of data and was quite accurate. And they wanted to learn a cheaper, faster model that could mimic the teacher but wasn't as expensive as the teacher. And so they came up with this concept of the teacher model is being used in inference mode. It takes the data, it makes a prediction. The student model is in training mode, and the student model makes a prediction. And there's some hard ground truth that's going into the loss function, for the stochastic gradient descent to improve the student's parameters. And there's also this loss function that's a component of the loss function that's coming from the prediction from the teacher, but that's a soft input, okay? And it turns out that this model basically works. And what we're doing is working on replacing that teacher, which originally was conceived of as another deep learning network, just more sophisticated, with something completely different, with, in this case, a simulation. So the simulation now has access to the data. It simulates, predicts some property of that data, and that then is fed into the training paradigm, again, as a feature in the loss function, a soft feature. And this model starting to work. We have some collaborations where we're applying this in cancer. I don't have time to go through this detail, but this slide is showing us where in the middle we've got simulations that are basically using classical biophysics to model the interaction of small molecules with kinases, and we're wrapping it with machine learning to try to learn these other relationships in the context of the ground truth coming from the simulations. And again, the best performance so far that we're getting from the deep learning is comparable to what we're getting from the simulations alone. So we think this together will be good. The second connection, that arrow going the other direction, is quite different. So so there's several different ways you could view that. One is the machine learning is somehow controlling the simulation. And that's an interesting story. It's a whole other set of talks. The example that I want to show, because it's kind of a cool result, it's not ours, it's from Microsoft. is where the machine learning is kind of replacing components in the simulation. So there's this idea in approximate computing, which is a whole field in and of itself, of various ways of devising cheaper, faster approximations, either because your system's unreliable or you want low precision, to feed into some, say, simulation or some process that gives you a knob in some sense of cost versus accuracy. And the idea here is you can do the same thing with deep learning models. So you can take some model, some code that has internally, inside it, some first principles function, and you essentially run the simulation, capture the input-output of that function, and then you use that relationship, you use that data to train a model that then replaces that function. Okay? And the idea is to try to explore this notion of trade-off between accuracy, power, performance. Okay? And so the Microsoft study, they picked a bunch of, I don't really want to call these applications, they're almost like benchmarks, but you got things like black shoals and some fluid mechanics and some other stuff. And the kernel in there, are traditionally either some PDE kernels or simulated annealing or some image feature extraction. They either map those into either a classification problem or some approximation effort, and then they replaced that kernel with a machine learned function. And they did some literature searching to try to find reasonable starting points. And here's kind of the data flow. So they ran the code, produced this data, they trained the network, they then ran a code generator that stuck the network calls in there as a replacement to the original function, but called the original function as well so they could calculate the error. And what they got was something quite interesting. So on average, okay, they have an error of something like 7%. And they could probably do better by changing the thing. But they also got a speed up, about maybe, in this case, a little over 2, and a power reduction. Right? So you got 3x improvement in power, 2x improvement in speed, in exchange for 7%. Well, in some problems, you don't want to give that 7% up, but in some problems, your model is probably not even accurate within 7%, and so who cares, right? So this is pretty interesting, this idea that we could embed machine learning in simulations and make these trade-offs, right? And that could drive high-throughput machine learning architectures at some level. Okay, so now cancer comes back into the picture. So starting in 2015, there was a set of conversations between DOE and the National Institute of Health, particularly the National Cancer Institute. This is between Secretary of Energy Ernie Moniz and Obama administration and the Director of the National Cancer Institute, Lowy, at the time. And the idea was, could we form a partnership between DOE and NCI where NCI would get access to the computing and math expertise in the labs and the big computers we have, and what we would get from NCI would be a completely different kind of problem than what DOE traditionally works on. And this was done in the context of the Cancer Moonshot project that Joe Biden was leading. I love this picture, Joe. And the Cancer Moonshot concept was to try to do 10 years of cancer research in 5 years. Okay, so this kind of acceleration of the research. And the idea, one of the key ideas behind this is to figure out how to make personalized medicine, precision medicine, personalized personalized chemotherapy, whatever you want to call it, it's the same thing. It's basically, instead of treating all the humans the same, trying to use molecular markers, images, transcripts, genomes, SNPs, and so forth, build predictive models that allow us to now stratify the population and stratify the tumors in particular, and then align treatment options for that stratification. And this is fundamentally based on the idea of either identifying signatures that a specific gene patterns in the tumors that are predictive of the drug response, or machine learning, or some combination of that. So there's 3 projects that got launched. I'm driving one of the projects in drug response prediction. There's another one led by Fred Straits at Livermore on simulating the signaling cascade in the RAS cancer pathway, which is in about 30% of cancers, kind of the nasty ones that we can't treat. And this idea of global treatment strategies was led by Gina Trossi at Oak Ridge. And then later, after starting on this for about 6 months, we decided that all three problems had a need for scalable machine learning. And this is around the time that the exascale computing project was spinning up. And so we wrote a proposal called Candle to build a scalable machine learning infrastructure that meets the needs of these three cancer problems. And I don't really have time to do a talk on that, but what we're trying to do here is be able to scale up the machine learning on future HPC platforms. It's all built on top of open source frameworks, but to give us some insight as to what has to change in these architectures going forward and bring in vendor collaborations and multi-lab collaborations. So we're now in just starting year 2. It's going extremely well, and we'll have a workshop on this at Supercomputing. So if you're there, you can come and talk to us. At a very high level, the Candle software stack has 4 layers. So it has a very low-level layer that talks to the hardware. This is typically done by the vendors tweaking things. Sometimes we can improve that. There's the tensor graph engine that's we're building on top of the big open source frameworks, then a scripting layer, and then a data management and hyperparameter search layer. There's a lot going on in the deep learning framework space, and this slide tries to collapse our decision-making process. So the red columns are the features that we wanted in our framework, and the green arrows green boxes are the 3 choices that collapsed out of that. And Theano was, of course, one, but Theano's been end of life in some sense. So TensorFlow, MXNet, and CNTK. So CNTK is Microsoft, MXNet is Amazon. Remember the slide with the 2 pokes, right? And then TensorFlow, of course, is Google. TensorFlow right now is kind of 10x the adoption of everything else, but we're trying to hedge our bets there. And we can build models that are actually doing quite well. I'll show you an example of that. So here's a cartoon where we have gene expression data on the left and a multi-layer network that has the first couple of layers being convolutional layers. Now, convolution is typically used in 2 dimensions in image classification, image recognition problems. In the cancer case, even though I've drawn this as a 2-dimensional plot, in fact, gene expression is kind of 1-dimensional or 0-dimensional. I mean, it's just a list of genes, basically, and expression levels. So we've adopted a 1-dimensional version of convolution to recognize features in the gene expression space, and then we have put a classifier, a fully connected set of layers on top of that. And we did some experiments, this is stuff from last year, where we were, at first, this kind of blew our mind that this worked, because convolution, intuitively, there's no particular reason why it should work in this case. And it turns out that it was working, but it was kind of an illusion. So what happens is the convolution will learn these features very quickly, and so we get fast convergence, but the ultimate convergence is about the same as for the network as if we ripped off the convolution, because the fully connected layers will eventually learn the same features. They're just kind of very slow at learning it. So that was kind of an insight. The current best performing model we have is much more complicated than that. It has what we call towers. So these are fully connected layers with residual connections, as skip links that jump layers, but are partitioned in the same way that they don't talk to their neighbors. And so we have these towers for gene expression, proteomics, microRNAs, and then we're learning properties of the drugs using these drug descriptor vectors that we compute. And then this stuff gets concatenated and merged through a set of classification layers that also have this kind of skipnet structure to them. And that network, you'll hear more about this if you come to Supercomputing Workshop, is outperforming all current models that we know about. It can explain about 92% of the variance in the data, and is getting about a 90% accuracy in ordering the drug combinations, which is kind of blowing our mind. So there's probably some bug. So, but what we're trying to learn from that is the following. So what we're doing in DOE is trying to figure out, okay, the future is not just traditional HPC, it's HPC merged with some kind of scalable data analysis. and deep learning, and so we want our future machines to be kind of good at that green box, okay? We might have to give up a little bit of something on the edge, but we're gonna gain more by bringing this bigger scope. If you read HPC Wire or the recent news, I won't call it fake news, but we're neither confirming nor denying anything that's in the story, that we have this machine called Aurora. It, for reasons that are complicated that I would need a lot of scotch to tell you, there's a version of this that will be deployed in 21 that's going to be the first US exascale machine. And we're trying to make this into a balanced architecture that will support simulation, data, and machine learning. And we call these the 3 pillars. They're not very imaginative. People hate the pillar word, but we don't have a better version of it. I want to call it 3 feathers or something like that. But, so it allow the integration of these capabilities, but also allow you in some sense to write applications that can mix and match. That's our vision. Of course, there's lots of applications that fit historically narrowly in each of these slices. I won't go through the list, but traditional simulations, big data where we've got typically streaming data off of large instruments, in some cases where we're iterating over that, and then deep learning. And of course, there's a lot of excitement over here, but they're just as important in this middle section. And recently, we've been doing a lot of design work on this machine, and one of the criteria for hitting exascale in the US is that we want to demonstrate a 50x performance improvement over today's 20 petaflop class machines. And so we've been doing a lot of simulation and analysis of these applications on this kind of novel architecture that we're building. And these are the working multipliers that we've come up with. And these are pretty solid numbers in the sense that they're going to be written into our contract with Intel and Cray. Remember, where's Anthony? Right, yeah, okay, they're going to sign up for these numbers, maybe. So we're seeing in the simulation applications, we're above 50 data, depending on what it is, above 50, in some cases as high as 100. And in the machine learning, in some cases, we're 160 times faster than the 20 petaflop machines, and this is without yet even dropping into like FP16. So we're pretty optimistic that we have a design point that can do it. And the challenge, and aside from the hardware, is in the software stack. So the software stack has to deal with the fact that the things that are important in these different pillars, in some sense, are quite different, right? I won't go through it in detail, but in simulation, just a thing about I/O for a second, usually you read much less than you write out, and most of the output you write out in simulations you never look at, okay? So that's a useful thing. In big data applications, both input and output are important. Output by design is used because often you're plugging things together in a pipeline, so you need to have balance there. And the output of these things is data, right? And in the deep learning, you're doing a lot more reading than writing, right? And the output of the enterprise is actually models, not data. Now you've got diagnostic data, and then you've got all kinds of differences in the arithmetic, the software stack, and so on. So the real challenge that we're working through is how to build some kind of a unified software stack that handles the resource management and allocations of stuff in a way that we can combine frameworks. And anybody who's tried to build TensorFlow on our HPC machine, if they still have any hair left, will realize that this is actually very hard, that the traditional way of operating HPC, where the systems administrators have kind of like the keys to the missiles or whatever, and don't let users to muck around with the software stack, except for in their own user space. But so to build something that actually would allow you to run Spark and Apache data analytics, as well as the deep learning frameworks with all the weird versions that are popping every day, and traditional libraries that are incompatible with everything else, is a big challenge. So trying to figure out how to do this, what's happened in the commercial world is people have just bailed to containers, mostly. But containers actually have a really hard problem in scaling on HPC architectures, and so this is one of the things. So, at a vision for this is something like this. Apologies to Bob Wisnowski, who I stole this slide and edited, so can't tell, but the idea at the top is, all these classes of applications, and to have the runtimes that support each of the three pillars hosted by some kind of multi-resource domain manager that knows how to do the right thing under the covers, including virtualization or bare metal, depending on what it is you're trying to do, right? So this is what we're trying to get to, and everybody gives us money, sort of, not enough, and I'm done with that. So I'll answer questions until you throw me out. So yeah.
Let's thank Rick. And we do have a few minutes for questions, so just signal that you want to ask a question, and we'll get a microphone to you. So there's one coming over here, in the middle somewhere. Okay, there we go. No, wait. There's one here first. Yeah.
Sorry. Thanks, Rick. I was curious. You're writing into the contract about performance numbers, but I was wondering if you're going to write in energy. My understanding is the energy requirements for running these things at high speed is more of a concern than the actual performance.
Well, we care about both. The energy, you can care about energy for lots of reasons. Fortunately in Illinois it's either nuclear or wind, so we don't have too much of a carbon problem. But yeah, in the time frame in 21, this kind of a machine, a sustained exascale class machine, is between probably 30 and 40 megawatts, and that's way more efficient on this new architecture than anything that we can point at currently. The big challenge for that is just the cost of power. It's not the impossibility of bringing that much power into a machine room. It's simply the annual operating cost. So I don't know if that answers your question. I mean, so we want to hit these performance goals because our science is kind of benchmarked against achieving forward-looking performance. In large DOE labs, I mean, something that draws 30 megawatts is big, but it's not bigger than Fermilab. For example, Fermilab is 60 megawatts, right? So, so we're concerned about power. If you've got any bright ideas on how to reduce it, we'd love to hear them.
Yes, thank you. I want to know a little bit more about using the machine learning, deep learning, together with the simulation part. So is it kind of similar with regard to the reinforcement learning? Like you use these simulation results to guide through the deep learning part?
So the teacher-student paradigm is not like reinforcement learning because you're, in fact, getting input from the teacher, in this case the simulation, internally in every mini batch, right? So whereas in reinforcement learning, the feedback is much slower, right? Now it doesn't mean you couldn't use it in reinforcement learning, so I think there are scenarios, particularly in terms of steering simulations, where reinforcement learning is probably the right way to think about it. But what we've been focusing on is this much more tight coupling that's used during training.
Oh, okay. I think there one challenge for deep learning is it is not very scalable. When we move into petascale, how do you make this really become scalable in that kind of
So
machine?
the way we think about scaling in deep learning is through three levels. So model parallelism, where you take a single network and you try to partition it across multiple compute units, and that typically is being done within a shared memory node across multiple GPUs or nodes or something like that. Then data parallelism, where you're replicating the model and you're essentially partitioning the training data in every epoch and computing you do a reduction to compute the gradient updates. And so in model parallelism, we think that at least in the modest scale models that people have historically been building, that you're unlikely to get a speed up, or it's unlikely to be reasonable to expect a speed up more like maybe 10, maybe 100 at most. Data parallelism, if you've got enough training data and it's well behaved, people have been successful up to 1,000, maybe 8,000. What happens is you have to really be careful about convergence, and so there's no point in scaling if your convergence goes bad. So we tend to think of data parallelism again kind of in the order of maybe 100 is routinely achievable. But the big source of concurrency is in hyperparameter optimization. So once you get a model that more or less works, you still have hyperparameters. That is not the internal parameters of the network that you're learning, but the things like the learning rate and the structure of the network and so on. And trying to search that space is challenging, but there's a huge amount of concurrency there. And so our infrastructure takes all three of these, and we can show that at least in the foreseeable future, we can fill up machines. So we have no problem using 100 million cores, for example, by using the combinations. I think one thing that will change there is we're starting to see in the deep learning community progress towards these very large multitask networks. 3 or 4 papers in the archive last year about this, where these networks are kind of orders of magnitude bigger than single task networks, and they have more complex sparsity structure. And so we may end up moving ultimately towards a world where we have, instead of one network per problem, we have these big networks that get trained simultaneously on many problems. They're kind of multi-tenanted in the sense that multiple applications might be querying them at the same time. They'd be online, so they'd be both inferring and training at the same time. And we think these kind of networks would be persistent. This is like the inklings of the singularity here, but these things would be persistent and very large. I mean, they might be 1,000 times larger than the current networks. So I can point you to some papers on that if you're, not ours, but that people are working on. So.
Let's thank Rick again for a fantastic talk. So.